Hello everyone, and welcome to lecture 3 of Comp 0003. The plan for today's lecture is to carry on talking about propositional logic, which is our first main topic. The plan for today's lecture is the following one. First of all, I'm going to recap the main points from last lecture on the syntax and semantics of propositional logic formulas, the semantics being done using truth tables. Then I'll give a slightly different way of presenting the semantics, and I'll also talk about some useful equivalences on propositional logic formulas. And then lastly, we'll see how we can use these equivalences to rewrite propositional formulas in various kind of useful ways. So I don't think we'll be coming back to me probably for the rest of the lecture. I don't think there's going to be any need. So let's go to the slides now, and I will see you at the end. Okay, so let's start just by recalling the syntax of propositional logic. I've put everything all on kind of one slide in one go here because it all should be familiar from last time. First of all, remember that we assume an infinite set of proposition letters or variables that will stand for propositions, and I'm generally writing capital letters for these, so P, Q, R, and so on. And then we have a grammar, a so-called grammar for propositional logic formulas, which is kind of given inductively, or sometimes we might also say recursively. So a formula A of propositional logic is either a proposition letter by itself, or it is the negation of something which is a propositional formula, or it is the conjunction of two propositional formulas, or their disjunction, or an implication, or an equivalence. All the binary connectives are always placed inside parentheses, and that's so that we can disambiguate the order in which we're supposed to read them. So, for example, A and B in brackets or C is not the same formula as A and B or C in brackets. So it's important that we keep those parentheses there most of the time. However, we can obviously drop the parentheses around the very outside of formulas, so we don't have to have the outermost parentheses. That's okay. And we don't use parentheses around negations either, so we write not A rather than not A in brackets. And the reason for that is that we have a kind of assumed precedence order where not binds tighter or has a greater precedence than any of the other connectives. So that's syntax, simple enough. And now let's start with the semantics. Remember that I said that, let's write L for all the set of propositions that occur in a given formula A. And then evaluation for a formula is an interpretation of each of the propositions in A, in other words, for each letter in L, as being either true, 1, or false, 0. So that means evaluation is really a function from the letters of a formula to the set 0 and 1. We also saw last time how it is that evaluation for A determines its overall truth value using the truth tables that we gave for each connective. So in other words, if we know what are the truth values of the propositions occurring in a formula, then we can also determine, using the truth tables for each connective, what is the truth value of the overall formula. So, although I don't propose to show all of the truth tables for all of the connectives again, I thought it was worth taking a look at the truth table for implication one more time. Remember that A arrow B, or A implies B, means that if A is true, then B is also true. So, the truth table for A implies B is here, and remember that if A is true and B is false, then A implies B is also false, because you have A and you don't have B, so you definitely don't, in that case, have A implies B. In all other cases, the formula A implies B is true, which means that A implies B is equivalent to not A or B, because if A is false, then A implies B is true, and if B is true, then A implies B is true as well. And that's exactly all the cases in which A implies B is true. One way, we discussed this a little bit last time, but I think it's also worth thinking about it in the following way. One way of understanding why the truth table for A implies B is the way it is that it's a way of kind of saying we only really care about the cases in which A is true. We don't care at all about the cases in which A doesn't hold, because A implies B means if A. So of course you don't really have to worry about the cases when A is false. So if we think about the cases when A is true, which are just these two lines down here, then in those cases, A implies B is true just when B is true. So if A is true and B is false, then A implies B is false, and if A is true and B is true, then A implies B is true. So in some ways, it's a bit like saying, if I ask you to prove that if a number is greater than 2 and it is also a prime number, then it must be odd. I mean, that's a trivial example, but you wouldn't proceed in that case by saying, oh, let's think about the number 8. Well, no, because I only asked you to think about numbers which are both greater than 2 and also prime. 8, of course, not being a prime number, so it's not something that you have to worry about. You have nothing to prove there, so we can kind of say that the statement, if a number is greater than 2 and prime, then it's odd. It somehow excludes automatically all the cases where the number is not prime or not greater than 2. So I'm kind of saying you're let off the burden of proving anything in those cases. So in particular, we have some statements. Here's a few examples here. The statement, if 6 is prime, then anything, any statement at all. That's a true statement for the reason that 6 is not a prime number. I've said, well, think about the case where 6 is prime. Well, there are no cases when 6 is prime, so it's trivially a true statement. It's true, but not very interesting. Similarly, the statement, if anything at all, then 7 is prime, is also a true statement, because just for the reason that 7 is a prime number. So it will continue to be a prime number, whatever else happens to be the case or not. Again, so these two statements correspond to the case. The first one where the case where A is false, and the second where the case where B is true. On the other hand, the statement, if 7 is prime, then 6 is prime, is obviously a false statement, because 7 is a prime number, but 6 is not. By the way, people have worried about these kind of readings of implication for a long time and proposed various kind of logical techniques to get around it, although I think it's safe to say that none of them would be very satisfactory. But these so-called paradoxes of implication, classical logic implication is sometimes called material implication, and so sometimes it's called paradoxes of material implication, but it's a name for a whole bunch of consequences of the definition of implication using that truth table, which are correct according to the truth table, but they don't seem to really correspond to the way that we use the word if in English. So, I mean, you can see that these are valid just by reading the truth table. Since A implies B is true whenever B is true, we have that B implies A implies B is a valid formula. And you can check that using the truth tables again. So, yeah, I mean, if a formula is true, B, then it is implied by anything. And we've already seen that must be the case according to the truth table. We've also saw the so-called paradox of entailment. If A is not true, if not A, then A implies B. And as we discussed, in some ways this can be read as saying, if you already know that A is false, then the statement A implies B becomes empty. There's nothing to prove because you already know there are no cases in which A holds. Another way of thinking about it is that if you have not A and then if you have A, well, then you have a contradiction, which is impossible and from which anything follows. So, I mean, again, you can see that this is correct according to the truth table, because when A is false, not A, then A implies B is always true. And then you have even other more weird seeming consequences. So, for example, the formula P implies Q or Q implies R is a valid formula as well. So for any statement, any three statements P implies Q, for any three statements P, Q, and R, either P implies Q or Q implies R. And the reason this is valid is because by the law of excluded middle, we have either Q, in which case P implies Q is true, or not Q, in which case Q implies R is true. But yes, I mean, it does seem very strange, especially when you translate it to English. So the last thing I wanted to recap today was the notion of satisfiability and validity of proposition logic formulas. Remember that if V is a valuation for a proposition logic formula A, then we write this notation, V double turnstile A, to stand for V satisfies A, meaning that when we take the valuation V and use the truth tables for the connectives to evaluate the truth value of A in that valuation, then A turns out to be true. In other words, it has truth value 1. If A has truth value 0 in the valuation V, then we write instead V not satisfies A. In other words, this double turnstile with the line through it. And the formula A is called satisfiable if there's at least some way of making it true, which is to say that V satisfies A for some valuation of the proposition letters. If there's no way of making it true, in other words, if it turns out to have truth value 0 for all possible valuations, then it is called unsatisfiable. Similarly, the formula A is said to be valid if it is true in all possible valuations. In other words, if all lines of the truth table turn out to be 1, or if V satisfies A for all possible valuations V. If there's at least some way of making the formula false, then the formula is said to be invalid. And as I said and asked you to prove last lecture, a formula A is invalid if and only if the formula not A is satisfiable, and in a similar vein, A is unsatisfiable if and only if not A is valid. Now, although we gave the notion of V satisfies A in terms of the valuation V and then truth tables for the connectives, we can also give a direct inductive definition of the relation V satisfies A. And this will be given by what is called structural induction on A. So in other words, we will have a case of the definition for every possible form of the formula A. So when it's a proposition letter, when it's conjunction, when it's a negation or an implication, and so on. And it's inductive in the sense that we assume inductively that we already know whether or not V satisfies A and B, where A and B are the components. And then we can, in terms of that, we can then say whether or not it satisfies, for example, the conjunction A and B. So first of all, I'll say what it means for V satisfies A for the smallest formulas, which are propositions. And then I'll go on to say how V satisfies A for compound formulas built up from connectives are defined in terms of their arguments. So in the case where A is an atomic formula, or in other words, a proposition letter P, for example, well, we already know that the valuation tells us directly whether or not a proposition letter is true. Remember that valuation is just a map or a function from the proposition letters of a formula to truth values 1 and 0. So a formula P is satisfied by the valuation V if and only if V of P is equal to 1. Next, suppose that we have the case of a negation. So we assume inductively that we know whether or not V satisfies the formula A, and then we can say whether or not the valuation V satisfies the formula not A. So a formula satisfies not A if and only if it does not satisfy the formula A. And remember that this completely agrees with the truth table, because when A has truth value 0, then not A has truth value 1, and vice versa. So really this is just a shorter way of writing down what's already contained in the truth table for negation. Similarly, V satisfies a conjunction of formulas A and B if and only if it satisfies the formula A and it satisfies the formula B. A valuation satisfies a disjunction of formulas A or B if and only if V satisfies A or V satisfies B. And when I say or here, I mean or in the inclusive sense, meaning V satisfies A or B or both. In the case of an implication, valuation V satisfies the implication A implies B. Well, remember that A implies B is equivalent to the formula not A or B. So a simple way of writing down the relation for an implication A implies B is to say that V satisfies A implies B if and only if V does not satisfy A or it does satisfy B, again, or both. Because remember that when A is 0 and B is 1, then A implies B is still 1 as well. Lastly, and in a similar way, remember that a by-implication or an equivalence, A if and only if B, means that A and B have the same truth value. So a formula V satisfies a by-implication A if and only if B. That means exactly that either V satisfies A and B, or it does not satisfy A and it does not satisfy B. And it's quite easy to see, just by examining the truth tables for each connective, that this definition is just another way of writing down the definition that we gave already in terms of the truth tables for the connectives. So here's something which is really just a kind of quick remark or observation. Although propositional logic, the way we've defined it, has got proposition letters and then negation, conjunction, disjunction, implication, and by-implication as its connectives, we actually don't need all of those connectives, strictly speaking, in order to define all the fundamental concepts of propositional logic. In particular, if we have only proposition letters, negation, and implication, then we can define all the other connectives. So when I write this symbol here, I mean equal by definition. So it's a definitional equality symbol. And so rather than having disjunction, for example, as a connective in the logic, I can just say the formula A or B is really just an abbreviation for the formula not A implies B. And you can check for yourself that not A implies B, at least if you've transformed A and B in the same way, it doesn't contain any any disjunction symbols either. It only has negation and implication in it, and has exactly the same truth table as A or B. In a similar way, you can define conjunction and by implication using only negation and implication. And I've decided to leave these two as exercises for you to do at home, but it is true. And there's nothing very special about negation and implication here. You can actually get away with using, for example, only negation and conjunction, or negation and disjunction. And if you take those as your basic connectives, then you can define the other ones as well. Also an exercise. Here's a question on the slide. Could we get away with just conjunction and disjunction? Well, I mean, I suppose the hint here is the answer is no. And this is also kind of an exercise, but just as a little hint, I think the first thing to think about is how would you define negation using only conjunction and disjunction? Could you do it? The answer is no. And if you play around with the truth tables for a little bit, I think you will discover why not. Next, I wanted to talk about some useful equivalences in propositional logic. So this is just going to be a big list of equivalences. When I write equivalence here, it means the same thing as by implication, really. I mean that the two formulas on the left and right have the same truth table. So I think most of these will be very easy for you to recognize that they are equivalent, and when you have any doubt about it, then you can construct the truth table, of course, and check for yourself. So our first equivalence is that not A is the same thing as A. And this is very easy to see. I mean, if you say it's not the case that it's not the case that A, well, that's really just the same thing as saying A. And of course, when you write down the truth table for negation, it just flips the truth values backwards and forwards. So of course, if you flip it twice, then you get exactly the same thing again. Next, we have the so-called commutative law for conjunction. So A and B is the same thing as B and A. And the same holds of disjunction, by the way. A or B is the same thing as B or A. Beware that it's not true of implication. So A implies B is definitely not the same thing as B implies A. But for conjunction and disjunction, and indeed for by implication as well, all those connectives are commutative. In other words, it doesn't matter which way round you write the formulas. In a similar way, bracketing does not matter for conjunctions. So if you have A and B and C in brackets, it's exactly the same thing as writing A and B in brackets and C. So in other words, the bracket, I mean, really all you're saying is that you have A and you have B and you have C, and the order you bracket it doesn't matter at all. The same is true for disjunction, and actually the same is true for by implication as well. Again, it's not true for implication, so be careful there. So that justifies, I mean, if you write down A and B and C without brackets, although strictly speaking, according to our syntactic definition, that would not be a propositional formula, it can still be read unambiguously because of this equivalence. So for that reason, in the future, when we write down a conjunction of three things, I might actually quite often drop the brackets, and then I'm implicitly relying on this law. Next, we have the so-called distribution of conjunction over disjunction. So consider the formula A and B or C. Well, that means if we have that formula, then we definitely have either one of two things. We either have A and B, or we have A and C. And of course, we might have both, but that's fine because B or C is inclusive, and it's inclusive on both sides. Similarly, if I have A and B, or A and C, well, there are two cases. If I have A and B, then I have A and B or C, because if I have B, then I definitely have B or C. And similarly, if I have A and C, then I have A and B or C. So the equivalence works in both directions. So this is kind of a way, if you have a disjunction inside a conjunction, you can kind of see that here in the syntax tree, the conjunction would be higher in the syntax tree than the disjunction. But this is a way of pushing the disjunction out of formulas, or into formulas if you use the equivalence in the other way. Oh, sorry. We actually have a similar law the other way around. If we have A or B and C, then it's definitely true to say that we have A or B, and we have A or C. In the case that we have A, we have A or B, and we have A or C, so we definitely have their conjunction. On the other way around, if I have A or B and A or C, well, in that case, either I have A, in which case I have A or B and C, or I don't have A, in which case I must have B and I must have C, in which case I have B and C, and therefore I also have A or B and C. So this is a way of distributing conjunction and disjunction, but now in the opposite direction. Next, I think we already saw this law before, that controls sort of negation, disjunction, and conjunction. So we have not A or B is not A and not B. That's easy to see, again, from the truth table. They're called the De Morgan laws. So if I don't have A or B, then it must be the case that I don't have them both. I don't have A and I don't have B. Similarly, if I don't have A and I don't have B, then I obviously can't have A or B either. And the same is true if I flip the rules of conjunction and disjunction. Not A and B means I must have, well, I don't have both of them, so I must not have one of them. So either not A or not B. Similarly, if I have not A, then I can't have both A and B. And if I have not B, then I can't have not A and B. So if I have not A or not B, then I have not A and B. So again, you can also see that this plays the role of moving disjunction either into or out of formulas. Obviously, if you're going from left to right, then you're pushing the disjunction further down into the formula structure. And if you're going from right to left, then you're kind of pulling it out somehow. Next, well, I mean, of course, we have already explained several times that A implies B is the same as not A or B. And that also means that the negation of an implication, not A implies B, means precisely A and not B. Again, this is very easy to see from the truth table. A implies B is only 0 in the case that A is true and B is false. So it's very easy to see this equivalence as well. This next one's a little bit more interesting. It is sometimes called the modus tollens principle in Latin, and I'm not sure exactly what that translates as, but it says that the two formulas are equivalent. A implies B is equivalent to not B implies not A. And to see why this is equivalent, consider a statement such as, if it's raining, then I'm in the pub. Well, I mean, there's this kind of common fallacy that some people will go, oh, well, then if it's not raining, you're not in the pub. That's not true, because the statement, if it's raining, then I'm in the pub, doesn't say anything at all about what will happen if it is not raining. However, we can definitely say, if it's the case that if it's raining, then I'm in the pub, then for sure, if I'm not in the pub, then it's not raining. Since I said that if it was raining, I would be in the pub, if I'm not in the pub, it follows that it can't be raining. And the same is true exactly in the reverse direction. In fact, you can think of that just by using double negation implication, I can say that not B implies not A by the left to right equivalence is the same as not A implies not B, which by double negation elimination is the same as A implies B. So the reasoning works in both directions. And finally, I think we've already seen a few equivalences involving by implication. But if we have A if and only if B, then that is exactly the same as saying A implies B and B implies A. In fact, this is exactly the technique that we use in proofs as well very often when when you're asked to establish an equivalence or a by implication, then often the easiest way is to saying if and only if, or an equivalence, is really, you have to establish two directions. First of all, assume that A and prove B. In other words, A implies B. And you have to do the other direction as well, assuming B prove A. So B implies A. Okay, so next I'd like to talk about a special class of propositional formulas that are of a particular syntactic form called disjunctive normal form, or DNF for short. Very roughly speaking, a DNF formula is at the top level a big disjunction of clauses, or so-called conjunctive clauses, and each of these clauses is a conjunction of literals, where each literal is either a proposition letter or its negation. So here I've given a formal grammar for DNF formulas on the slide here. First of all, we will define literals. So a literal is either a single proposition letter P by itself, or the negation of a proposition letter P. And here I mean that P can be any proposition letter, so things like Q or not Q and R, not R are all literals as well. Next, at the next level up, I'm going to define so-called conjunctive clauses, C. So C is either L, it's either a literal by itself, or it is the conjunction of a literal with something which is already a conjunctive clause. So in this way, we are allowed things like L and L, where the L's are literals, or L and L and L, and so on and so forth. So a conjunctive clause is a conjunction of one or more literals. Lastly, we have, and notice by the way that I'm not placing conjunctive clauses in brackets, or at least I'm not putting brackets around these conjunctions here, because by the associativity law of conjunctions, if I write literal and literal and literal, then it's unambiguous even if I don't bracket them. Lastly, I'm going to define DNF formulas. A DNF formula is either a conjunctive clause, which I will place in brackets because it's going to have some disjunctions around the outside. So it's either a DNF is either a single conjunctive clause by itself, or it is the disjunction of a conjunctive clause with something which is already a DNF formula. So let's see an example. So this formula here is a DNF formula that has three conjunctive clauses. The first conjunctive clause is a conjunction of three literals, P, not Q, and R. The second conjunctive clause is a single literal by itself, which, strictly speaking, according to the grammar above, I should have placed Q in brackets there, but it's still unambiguous if I don't, so there's no harm in dropping the brackets there. And the third conjunctive clause has got two literals in it, not P and not R. So it is a fact that given any propositional logic formula, it can be converted more or less automatically into an equivalent formula which is in disjunctive normal form. And before we see how to do that, I think perhaps it's worth talking about why you'd want to do that. Why are you going to mess around with this formula and put it in DNF? What would be the point? I don't understand, etc., etc. So the main reason for putting a formula into DNF or working with DNF formulas is that they are quite easy to work with automatically because their syntactic structure is so regular. In particular, it's a very, a typical kind of question is, given some possibly quite large propositional formula, is it satisfiable or not? In particular, if it's equivalent to false, then usually we can kind of throw it away straight away, or we can just replace it with a formula that means false. So it's useful for deciding the unsatisfiability of formulas or their satisfiability in the following way. First of all, given some arbitrary formula A, first step, convert it to an equivalent DNF formula. Now that formula will have, let's say, n conjunctive clauses in it, which I'm deciding to number as is standard in computer science from 0 to n minus 1. So this is a big disjunction of conjunctive clauses, C0, C1, C2, all the way up to Cn minus 1. Now, we can notice that if any one of those conjunctive clauses, Ci, let's say, is satisfiable, then the entire formula is satisfiable. In fact, and that's an if and only if. To satisfy a disjunctive formula, then it's enough just to show that one of the elements is satisfiable. And again, you can check that. Now, if we look at the structure of each of those conjunctive clauses, well, it's a conjunction of literals. So I've given these literals two indices, I, to remember that it's from the conjunctive clause Ci, and then within that 0, 1, all the way up to m minus 1. So I'm thinking that this Ci has got m literals in it. Now, how can we decide whether or not that conjunctive clause is satisfiable? Well, actually, we can notice that it is satisfiable if and only if there are no pairs of literals in it of the form P and not P. So we have to find some way of making all these literals true at the same time in order to satisfy the formula. And that's going to be the case. Well, we can find a valuation that does it every time that we see, say, P or Q or R. We should find a valuation that sets, P, Q, and R to the truth value 1. And every time that we see something like not P, not Q, or not R, we should set the valuation of P, Q, or R to 0. Now, that results in a proper valuation if and only if the valuation doesn't have to set the value of some proposition to be true and false at the same time, which is going to be the case exactly if this conjunctive clause doesn't contain some proposition letter and its negation. So, in other words, in order to decide whether a DNF formula is satisfiable, we just have to see whether we take all the conjunctive clauses and we see whether we can satisfy at least one of them, which is just a case of checking that it doesn't contain any sort of complementary or negated pairs of proposition letters. By the way, since we can decide satisfiability, and we know that satisfiability and validity are really closely connected, then we can also use this method to decide the validity or invalidity of formulas, because A is valid if and only if not A is unsatisfiable. So if I want to check that the formula A is valid, first of all, take the formula not A, second, convert not A to a DNF, and then, using the method above, check whether not A is satisfiable or not. If not A is unsatisfiable, then A is valid. And if not A is satisfiable, then A is not valid. So given an answer to the satisfiability of not A, then I can also get an answer to the validity of A. And the same would be true the other way around, but this is the right way to think about things for DNFs. Okay, so let's now talk about how one might actually go about converting a propositional formula to a DNF. Well, there are two main methods of doing this. The first of them, which we're going to talk about right now, is only appropriate for formulas that don't use very many propositional variables, because in that case the truth table is of a reasonable size. But when the truth table is of a reasonable size, well then a DNF equivalent to a given propositional formula can just be read off from its truth table. So here I've given the truth table for the formula P if and only if not Q implies R. So you see here I've done the normal thing of constructing an intermediate proof table column for the sub formula not Q implies R, and then so that's kind of easy to do. And then here, this line of the truth table, this column, is for the whole formula, and so we just look at all the lines in which P and not Q implies R have the same truth value. So that's the case in the first line and in the last three lines. So if we look now at all the rows of the truth table for which the formula has truth value 1, well, we can see here that there are 4 cases here in which that is the case, and indeed we can then just read off a DNF formula directly from the proof table. We can say that P if and only if not Q implies R is true, just in case either P and Q and R are all false, which is to say not P and not Q and not R, or if P is true and Q is false and R is true, and then 2 more possibilities that are given by these other rows. So each of these 4 possibilities corresponds precisely to a conjunctive clause of the DNF. The DNF formula will have 4 clauses, 1 for each line of the proof table that comes out to be 1. So the DNF is, as expected, not P and not Q and not R. That's the first possibility. Or, second possibility, P and not Q and R. Or P and Q and not R. That's the second to last line of the table. Or P and Q and R. So you'll see that this is indeed a DNF formula. It is a disjunction of conjunctions where every conjunction is either a proposition letter or its negation. So it's easy to see that that when you have the truth table for a propositional formula, then you can just read off the DNF straight away. Now, What happens though when the formula is too big for in order to be kind of easy to construct the truth table and just read it off? Well, in that case, we can use equivalences in order to kind of convert the formula into a DNF step by step. So here I'm going to give a sequence of steps for converting a formula to a DNF using logical equivalences. It's worth saying that you don't have to do them all in this order, but this is more or less any order of applying these steps will get you there eventually, and some sequences of steps might be a bit more efficient than others. But okay, I mean, the first thing we can think about if you have an arbitrary propositional formula is it has all these kind of connectives floating around in it that aren't even allowed at all in DNF formulas. So in particular, it might have some by implications in it, A if and only if B. Well, they're not allowed at all. We have to get rid of those. So we could consider replacing them, for example, replace them all with A implies B and B implies A. So we can get rid of all the by implications just by replacing them with a formula of that form. Or we could notice that since implications we're going to have to get rid of again at the next step, we could also replace it with another equivalent formula like A and B or not A and not B. Anything like that would work. Of course, doing it this way, you notice straight away that the implications are not allowed either. So you can replace A implies B with, for example, not A or B. And you can replace negated implications more quickly you could just replace A implies B and then you have a not A or B, and then you can do something about the negations later. Or you can directly replace not A implies B with the equivalent formula A and not B. The next thing that you'll notice is that we're only allowed negations at the level of literals. So we're not allowed negations outside conjunctions, and we're not allowed them outside disjunctions, and we're never allowed more than one. So fortunately, we have some equivalences that will let us move negations inwards in the formula. So to begin with, for sure, we can eliminate any double negations. So not A can be safely replaced by A. Great. If we have a negation outside a conjunction, not A and B, then we can push the negation inwards, because by using the equivalence that not A and B is equivalent to not A or not B. So this has the effect of kind of replacing the conjunction with a disjunction at the top level, but at least moving the negations down. And similarly, if we have a negation outside a disjunction, which also is not allowed in a DNF, then we can replace it with not A and not B. So if you repeat all these rules, then okay, you'll be a lot of the way there. You'll have a formula that doesn't have any by implication, doesn't have any implications, and only has negations if you repeat this often enough at the bottom level of formulas, so only outside of proposition letters. But you still might have the problem that the conjunctions and disjunctions are nested in the wrong way. So in particular, you can never have a conjunction outside of a disjunction in a DNF. Disjunctions have to be all at the top level, and then so it has to be a disjunction of conjunctive clauses. Now, to deal with this we can use our distribution of conjunction over disjunction. Remember, we have this law A and B or C is equivalent to A and B or A and C. So by applying this equivalence from left to right, and in fact, I mean that you should really apply all of these equivalences from left to right. I mean, they're valid in both directions, but I think for converting to DNF, you really want to apply them from left to right, because that's that will kind of get you closer to DNF-ness. So here, if you have a conjunction outside a disjunction, which is not allowed in a DNF, then you convert A and B or C to the formula A and B or A and C. This has the effect of moving the conjunction inside the disjunction, although you can notice that the formula gets a bit bigger. So in general, as you as you proceed, most of these transformations won't make the formula much bigger, but this last one will, in general. Just by the way, I should also remark that you can use the associativity laws to get rid of any unnecessary parentheses that are around sequences of disjunctions or conjunctions. So if you have, for example, A and brackets B and C, then the associativity law says you can drop those and it's still completely unambiguous. So that's safe to do. All right, so now let's see an example of how to construct the DNF of a propositional formula by using these equivalences. So here I've taken exactly the same formula that I had on the slide before last, where we constructed the DNF by truth table. And let's see how we can get to the DNF of this formula by using equivalences. So our first step is the formula is P if and only if not Q implies R. Now, as I said before, there's not one unique sequence of steps that will get you to the DNF, but I mean, I'm just showing you one particular or possible sequence of such steps. We probably won't do it all either. Then I'm going to leave you to finish off the rest once we get to a certain point. So the first thing we can notice is it's got an if and only if in it, and that's no good. So first of all, we'll use our equivalence for equivalences, or for by implication, to eliminate it. So we'll convert this by implication into two implications. P implies not Q implies R, and not Q implies R implies P. Simple. Next, we can notice that this formula is now full of implications, which are also no good. So I could rewrite them all at once, but I'm going to do it in two steps. I'm going to take these to higher level, or that they're occurring higher in the syntax tree implications, and eliminate them both. Remember that we have A implies B is the same as not A or B. So if I eliminate, let's see the next step, the first implication becomes not P or not Q implies R. And the second clause becomes not Q implies R or P. Again, just by using the rules. Next, I can see that I've still got two more implications to get rid of, so let's do those as well. So in fact, one I can sort of see is an implication, and the other one I can see has got a negation outside it. So although I could convert this second implication just using the same rules before and then do something about the negation, I'm going to do them kind of both at once. So the first implication becomes not Q or R, and the second implication becomes not Q and not R. Remember that not A implies B is the same as, not A implies B becomes the same as A and not B. So here our A is not Q and our B is R. Okay, so now we can see that we've a double negation has popped in here, so we might as well just get rid of it using our double negation principle. And so that's easy enough, very easy transformation. And then I can look and see that I now have a conjunction outside of a disjunction. And that's no good. In fact, you can see a couple of places where this has happened, but I'm going to choose to deal with this outermost one first. So we have a formula, this whole formula we can think of as being our A, and then we have something of the form B or C, where B is this formula here. So remember, this should become A and B or A and C. So as expected, we have A and B or A and C. Now, I'm using a different kind of brackets here just to make the formula a little bit easier to read. We're going to have a lot of like nested brackets here, so we'll try and make things a little bit easier on ourselves, but just by writing these different kinds of brackets to remind ourselves of the scope of everything. Next, if I look at this formula in the first set of the square brackets, I can see that we actually have something of the shape A and B or C, although it's written the other way around. So here, remember that A and B is the same as B and A. So I really have something of the same shape here. I have a conjunction outside of a disjunction of things. So you could read this as A or B and C, in which case you either have A and C or B and C. That's probably the best way of thinking about it. And so when I distribute this out, I get this now quite complicated looking thing, but I either have A and B, which is to say not P and not Q and not R, or I have this formula B together with this C. So I get or Q or R and not Q and not R. And then this other formula here hasn't changed, although I did manage to somehow accidentally change the square brackets here to curly brackets. It doesn't change the meaning of the formula, but I probably should have kept it the same. Sorry about that. Now, my highlighting here looks complicated, but it was only because I couldn't select a color for some reason. Here I just meant to observe that we have some associativity laws at work. So we have not P and not Q and not R, but of course we can drop these brackets here because that's just the same as not P and not Q and not R. We don't need any brackets there. And then at the higher level, we have this square bracket formula. In the first square bracket formula is a disjunction, and so is the thing outside it. So we have something of the form A or B in square brackets or C. And again, we don't, because of associativity, we don't need those brackets. So we can drop them to get something that looks a bit more familiar. So we have not P and not Q and not R, no brackets there, or Q or R and Q and not R, or not P or Q or R and P. So we can see already that actually we have now managed to generate at least the first clause of our DNF formula, which is not P and not Q and not R. I remember that corresponds to the first line of the truth table, and it was the first clause of our DNF. But we're still not finished. Here again we have a conjunction outside of a disjunction. So we have something of the form A or B and C, which is the same as A and B or A and C. So I'm going to leave this clause alone and this clause alone and just convert that one. And I get not P and not Q and not R, that hasn't changed. And then I get Q and not Q and not R, or R and not Q and not R. And then this third clause hasn't changed either. Now, by the way, these two clauses weren't in the original DNF, but you can actually see that they are unsatisfiable because they contain literals of the form. Here we have Q and not Q, so that's not going to be satisfiable. And R and not R are not going to be satisfiable either. So, I mean, it's actually a fact that these can, you could leave these in the DNF formula, it's perfectly valid, or you could, you could also kind of safely take them out by observing that the formula is that formula is unsatisfiable. If you have A and Q and not Q, well, A or Q and not Q, then that is exactly the same thing as just saying A, because the Q or not Q part is never going to be satisfiable. And then in the next step, we can see that we also have a conjunction outside a disjunction. We really only have this clause left to worry about. And so we would distribute the conjunction over the disjunction in the same way. But rather than show it here, I've reached the end of the slide. So an exercise for you to do at home is just to finish this off and generate the derivation. Now, although this might seem like quite a lot of work compared to the truth table method, and in this case it is rather simple in that the formula is becoming bigger, but it's not becoming unmanageable, I would say. And the process is somehow completely automatic. I mean, there is a decision about what order to apply the equivalences in to get you there, but there's no question about what equivalences you'll have to apply. And you know that if you just keep doing it, then that you're always going in the right direction and you will get there eventually. Which also means that it would be quite easy to construct a computer program that would do this, to take in a formula and output the same formula, but converted to DNF. You might want to try that if you fancy yourself as a programmer. Okay, the last thing that I'd like to say in this lecture before we kind of wrap up is that DNF formulas are kind of quite useful, but they're not the only possible normal form for propositional formulas. Remember that DNF is essentially a disjunction of conjunctions, but we could have done things the other way around. We could have written things, instead of as a disjunction of conjunctions, we could alternatively have written them as a conjunction of disjunctions. And indeed, there is another normal form for formulas called conjunctive normal form, or CNF, which is kind of like an inverse or dual of DNF. So we define literals as before, and now a disjunctive clause is given by this grammar for D. So a disjunctive clause is either a literal by itself, or it's a disjunction of a literal with something which is already a disjunctive clause. So a disjunctive clause is just a disjunction of one or more literals. And then a CNF formula is either a single disjunctive clause by itself, which I'll place in brackets, or it's a disjunctive clause conjoined, or the conjunction of a disjunctive clause and something which is already in CNF. Again, it's the case that every propositional formula has an equivalent formula in CNF that is logically equivalent and is in conjunctive normal form. Unlike a DNF, it's much harder to read a CNF formula off of a truth table. It's not quite so easy to do this, but we can get there by using equivalences. In fact, almost the same method as for DNFs will work, except that we have to apply distribution in the other way. Instead of pushing conjunctions inside disjunctions, we have to push disjunctions inside conjunctions using the other distribution law. CNF, I think, is not as popular as DNF, but it is quite useful for theorem proving. If you want to, so in theorem proving, we want to show a theorem, which usually means proving that a formula is valid. In other words, that it's true under all possible interpretations. So you can notice that if you have a formula which is a CNF and it's a conjunction of things, well, in order to make it valid, it's going to have to be the case that that all clauses are going to have to be valid as well. And for a particular disjunctive clause to be valid, then it cannot contain any literals such that you don't have the complement of that literal. So, for example, the formula, the disjunctive clause P or not P is valid because of the law of excluded middle, but the clause P or Q is definitely not valid because you can just take evaluation where you set either of P and Q to 0. So although CNF is not used quite so much, you can convert a formula to CNF using equivalences in the same way, and indeed you might be asked to do so in an examination situation. So watch out for that. All right, that just about wraps it up for today. And in fact, it concludes most of the important things we want to say about propositional logic. In the next lecture, we'll look at Boolean algebra, which is propositional logic with kind of different notation and looked at from more of an algebraic point of view. So it's a little bit different, but somehow is capturing much the same thing. In terms of the main things I would like you to remember about propositional logic, for sure, the syntax of formulas, the semantics of formulas, and the truth tables for how to construct a truth table for a formula, the notion of equivalence and remembering some of the useful equivalences between formulas, the notions of satisfiability and validity of formulas and how these are connected, and lastly, the conversion to normal forms. So, thank you very much for listening, and I will see you for the next time, Lecture 4. Take care.